Welcome, students, to the captivating realm of physics, where curiosity meets discovery. As we embark on this intellectual journey, I encourage you to explore the wonders of the universe, from the smallest particles to the vast cosmos. I invite you to view our latest video, which delves deeper into this fascinating subject. Kindly subscribe to our channel for ongoing insights and discussions that will ignite your passion for learning. Together, let us uncover the mysteries of nature.
Dear students, in this video we are going to study about prisms. Let us see what is a prism. A prism is a triangular block of transparent glass. It is bounded by three plane faces. The first face is rough, which is called base of the prism. The other two faces are polished, which are called refracting faces of the prism. The angle between the two refracting faces is called angle of the prism, or refracting angle, or apex angle, and that is represented as A. So here in this diagram, A represents angle of the prism. For equilateral triangles, this angle will be about 60 degrees. Now let us see what is angle of deviation produced by a prism. For that, let us consider a prism ABC. The faces AB, the AC are polished, and the face BC is a rough surface, that is called the base of the prism. But light ray PQ is incident on one of the refracting faces of a prism as shown in the diagram, that is here. So this is the incident ray PQ, and QR is the ray it passes through the prism, and the emergent ray is RS. So if this prism is not present, this incident ray PQ should have traveled straight like this. Because of one plane surface here made of glass, it gets refracted like this, and this ray again is refracted by the second surface. So this is the emergent ray, and the angle of deviation is measured between the angles of this incident ray. It should have gone straight, and the emergent ray. So we should extend this ray backwards, and that will touch the direct ray here. So this angle between these two rays, that is called the angle of deviation, represented by a letter D. Here I1 is angle of incidence, and I2 angle of, here this angle of incidence for this ray, and R1 and R2 their way angles of refraction. The A is the angle of the prism, which is about 60 degrees for an equilateral prism. The angles of incidence and refraction of the first phase AB are I1 and R1. The path of light inside the prism is QR. The angles of incidence and refraction at the second phase AC is given by R2 and I2. So that is represented here, R2 and I2. RS is the ray which emerges from the second phase. So this is the emergent. And the angle I2 is also called as angle of emergence. The angle between the direction of incident ray and the emergent ray is called angle of deviation D in a prism. So that is represented here in this part. The two normals drawn at the point of incidence Q and at the point of emergence R meet at point N, that is here. So when you are extending these two rays, they meet at this point N. The extended incident ray and the emergent ray meet at the point M here. And the angle of deviation D1 of the surface AB is given by measure of angle RQM equal to D1, and that's given by I1 minus R1. The angle of deviation D2 at the surface AC is given by measure of angle QRM, that's given by D2, and that is I2 minus R2. So the total angle of deviation D produced is given by this expression D equal to D1 plus D2. Substituting the values of D1 and D2 in the equation 6.83, we get D equal to I1 plus I2 minus of R1 plus R2, that's 6.84. And in the quadrilateral AQNR, here that is AQNR, that is a quadrilateral. two of the angles that is at the vertices Q and R are right angles. Therefore, the sum of the other angles of the quadrilateral should be equal to 180 degrees. That means my subtriangle A plus Q and R that should be equal to 180 degrees. And in the triangle Q and R1 plus R2 plus Q and R angle that's given by 180 degrees. Now comparing the two equations 6.85 and 6.86, these two equations, we get the angle of the prism will be equal to the sum of these two angles R1 and R2. So we should substitute this equation for the angle of deviation D, that's given by I1 plus I2 minus A. So this is the equation. Thus the angle of deviation depends on the angle of incidence I1, angle of emergence I2, and the angle of the prism A. But for a given angle of incidence, the angle of emergence is decided by the refractive index of the material of the prism. Hence, the angle of deviation for a monochromatic light, that is for a single color light, that depends on the following factors. The first one is the angle of incidence, next angle of the prism, next the refractive index of the material of the prism, which decides the angle of emergence. Then the angle of minimum deviation. What is that? Let us study about it. So here a graph is plotted between the angle of incidence I for various values of the angle of incidence 20 degrees, 40 degrees, 60 degrees, 80 degrees, like this. Angle of deviation is measured and a graph is drawn between these two, measuring these angles as 30 degrees, 40 degrees, 50 degrees, like that. So here we observe that the angle of deviation at first decreases with increase in the angle of incidence, and it reaches a minimum value D. And after that, as you further increase the angle of incidence, the angle of deviation starts increasing. So the minimum value of the angle of deviation, that is called as the angle of minimum deviation, represented by letter D. At this point, that is at the minimum deviation, the angle of incidence is equal to the angle of emergence, that is I1 will be equal to I2. Then the angle of refraction at the phase 1 and phase 2, that will be also equal, that is R1 will be equal to RT. So this is for the angle of minimum deviation position of the prism. And the refracted ray inside the prism is parallel to its base of the prism. So that also is remembered. Then we study about the refractive index of the material of the prism. So at this point of minimum deviation, I1 will be equal to I2 equal to I, and also R2 and R1 will be the same, that will be equal to R. Therefore, the equation 6.88 will become, that is, we can write it as D equal to I1 plus I2 minus A, or 2I minus A, as this I1 will be equal to I2. That means I will be equal to A plus D by 2. Similarly, the equation 6.87 can be written like this: R1 plus R2 equal to A. As R1 and R2 equal to R, we can write it as 2R equal to A. That means R, the angle of emergence R, can be written as A by 2. That is half the angle of the prism. So for an equilateral prism, this R value will be above 60 by 2, that will be equal to 30 degrees. So substituting the values of I and R in Snell's law, n is equal to sin I by sin R, we can write the refractive index of the prism as n equal to sin A plus D by 2 by sin A by 2. So this equation is used to determine the refractive index of the material of the prism. The angles A and D can be measured experimentally. Usually, the angle of, if you are using an equilateral prism, you need not measure the angle, then directly substitute as 60 degrees, and we should only find the angle of minimum deviation, which will be about 40 degrees here in this graph. So the refractive index for gas, we are using that, Here 60 plus 40, that is 100 by 2 sin 50, and here 60 by 2 sin 30. So simplifying this, the value of the refractive index of glass, you can get the value as 1.5. That will be the refractive index of glass usually. That is what you should remember. Next we will study about the dispersion of white light through a prism.
Welcome to This Explainer. Today, we're decoding the fascinating geometry of prisms. We're going to take a journey, tracing a single ray of light to see exactly how it reveals the very nature of the glass itself. Light might seem like pure magic, right? But once we break it down step by step, its secrets become crystal clear. Before we can understand this iconic, colorful split of white light, the kind of image you've probably seen on a certain famous album cover, we've got to strip everything back. To truly grasp the rainbow, we first have to master how a prism interacts with and bends just one single monochromatic ray of light. Here's our roadmap for today. 1. Meet the prism. 2. Bending light through angle deviation. 3. Finding the sweet spot. And 4. Unlocking the refractive index. Let's get right into it. Section 1. Meet the prism. So a prism isn't just some random chunk of glass. It's actually a precisely engineered tool. Picture a triangular block of transparent glass bounded by 3 flat faces. Typically, one face is intentionally left rough, we call that the base. But the real action? That happens at the other 2 highly polished faces. We call these the refracting faces, and the angle where these 2 polished faces meet at the top is absolutely crucial. We call it the angle of the prism, or the apex angle, represented by a capital letter A. Keep that A in mind, because it's going to be a huge player in our math later on. Section 2. Bending light, angle deviation. If we step into the shoes of the light ray, we can actually follow its journey. Imagine a focused laser beam. In step 1, it hits the first polished face at a specific entry point. That's our angle of incidence. Moving to step 2, because glass is denser than air, the light is literally forced to slow down. It alters its path, bending right through the body of the prism. Finally, in step 3, it hits the second polished face and exits back into the air. Since it's speeding back up, it bends a second time. This final exit trajectory is our angle of emergence. So the main takeaway here is that the prism forces the light entirely off its original straight-line path. Imagine drawing a straight line showing where the light would have gone if the prism wasn't there at all. Then, draw another line tracing where it actually went. The angle between those 2 lines? That is the angle of deviation, and we represent this total bend with a lowercase d. And that brings us to a surprisingly approachable formula. Honestly, you don't need to be a physicist for this one. The total angle of deviation, our lowercase d, is just the entry angle plus the exit angle minus the prism's apex angle. It's an elegant little equation that maps out exactly how the starting condition, the ending condition, and the physical shape of the glass combine to dictate the light's final path. Section 3. Finding the sweet spot. What scientists found is that changing the initial angle where the light hits the prism changes absolutely everything. Just look at this U-shaped graph. On the bottom axis, we're increasing the angle at which our light ray first enters the glass. On the vertical axis, we're tracking how much it gets deviated. Check out that curve. As you increase the entry angle, the total deviation actually goes down until it hits a very distinct minimum point right at the bottom. Keep increasing the entry angle past that, and the deviation shoots right back up. We call this distinct dip at the bottom the angle of minimum deviation. We use a capital D for this one just to set it apart from our general lowercase d. But here is the coolest part. This minimum point only happens when the angle of incidence exactly equals the angle of emergence. It is the precise moment when light enters and leaves the prism at the exact same angle. Visually, it is incredibly satisfying. Look closely at the ray in this diagram hitting that minimum deviation point. Because the entry and exit angles are perfectly equal, the path of the light inside the glass runs beautifully symmetrically, totally parallel to the rough base of the prism. It's basically a mathematical sweet spot of geometric harmony. Section 4. Unlocking the refractive index. Now, why do we care so much about finding that exact point of perfect symmetry? Well, when the light hits that sweet spot of minimum deviation, all of our complex math simplifies into this key equation. It lets us calculate n, which stands for the refractive index. Think of the refractive index as the optical fingerprint of a material. It tells us exactly how much a given substance naturally slows down and bends light. And look at the formula. You literally only need 2 pieces of information. the physical apex angle of the prism and the angle of minimum deviation we just talked about. Let's apply this to a real scenario from our source material. Imagine we're in the lab with an equilateral prism. That means all sides are equal, giving us an apex angle of exactly 60 degrees. Through testing, we find its minimum deviation is 37 degrees. We simply plug those two numbers into our equation. 60 plus 37 divided by 2 gives us the sine of 48.5 degrees on top. 60 divided by 2 gives us the sine of 30 degrees on the bottom. When you punch those signs into a calculator, you get 0.75 divided by 0.5, which leaves us with a final refractive index of exactly 1.5. And this is huge. Why? Because 1.5 is the universally known refractive index for standard crown glass. Think about that. We successfully used nothing but a single bent ray of light and some basic geometry to positively identify the very material sitting right in front of us. No chemistry required. Which brings us to a really fascinating final thought for this explainer. We've spent all our time focused on a single monochromatic ray. But what happens when you shine a beam of pure white light into the prism? White light isn't just one color, right? It's all the visible colors mixed together. And here is the secret to the rainbow. Every single color of light actually travels at a slightly different speed when it enters the glass. Because their speeds are different, their refractive indices are different. Violet light slows down the most, so it gets deviated the most. Red light slows down the least, meaning it bends the least. Since they all bend at completely different angles of deviation, they fan out. That's dispersion. It's the exact phenomenon that allows this mathematically precise block of glass to decode white light and paint vibrant rainbows across a room. We've seen how standard glass bends light to a factor of 1.5, but consider this. What sorts of invisible rainbows might exist if we swapped this glass for a diamond, or maybe a drop of water suspended in the sky? Thanks for joining me on this explainer, and keep exploring the amazing structures hidden all around us.